Here I have a Lego wheel. The diameter of this wheel is 62 millimeters. Give or take a bit, it's a bit hard to measure since it's rubber. Of course, if we multiply the diameter of this wheel by pi, we will get the circumference of the wheel, which is 194.78 millimeters. For the sake of simplicity, let's say that's 195 millimeters. Now let's take this wheel and have it cover a distance equal to its circumference. What do you think? How many rotations will the wheel complete? Now let's have the wheel rotate around an identical wheel. So again, it's covering the same distance, 195 millimeters. How many rotations will the wheel complete now? 1, 2 rotations. Okay, what just happened? Why did the wheel complete one additional rotation, even though it obviously covered the exact same distance? Is this the proof that magic exists? No. This happens because you think that the distance a wheel travels is measured here, at the contact point with the surface on which it travels. But that's incorrect. The actual point that determines the distance covered by the wheel is the center of the wheel. That's the reference point for distance because that's its axis of rotation. I can actually explain this a lot better with some gears. Here we have a 100-tooth geared rack, and here we have a 50-tooth gear. Since the rack has twice the number of teeth, its length equals 2 times the circumference of the gear. So if we rotate the gear along the rack, the gear of course completes 2 rotations. Now here's a 100-tooth gear. So its circumference is again twice the circumference of our 50-tooth gear. But now if we rotate the small gear around the larger gear, the gear actually completes 3 rotations, 1 additional rotation. Now let's take a negative of that gear, a 100-tooth ring gear. Again, the circumference is twice that of our 50-tooth gear. But if we rotate the small gear around the ring gear, it now completes only 1 rotation. If we observe the length of the contact surface, it's the same every time, 100 teeth. But if we plot the path covered by the center of the gear instead of the contact surface, we'll see that in the case of the toothed rack, the path is parallel and thus equal in length to the contact surface. So the gear completes the logical number of rotations, 2. But if we plot the path of the center of the gear when it's rotating outside the 100-tooth gear, we will see that it's no longer parallel to the contact surface. It's now concentric, i.e. circular, and sits at a distance from the contact surface. The length of the path covered by the center of the small gear is now obviously longer than the contact surface. Hence, 1 additional rotation is needed to cover it. If we observe the rotation inside the ring gear, we will see that the path covered by the gear center is obviously smaller than the contact surface, which means that it's shorter, so 1 less rotation is needed to cover it. And it is precisely this internal rotation that we are interested in, because here we have a potential to make a very compact and very potent gearbox. One of our gears sits inside the other. That makes it compact. Having the gear on the outside obviously occupies a lot more space. Now let's see what makes it potent. I want you to observe the hole in the center of the gear versus this arrow on the gear, which shows us how many rotations the gear itself has made. As you can see, when the hole in the center travels 1 full circle, the gear also completes 1 full rotation around its center. This is what we have seen already. Now let's see what happens if we increase the number of gear teeth to 75. As you can see, the gear now only completes 1/3 of a rotation, while the hole in its center travels a full circle, albeit a smaller one. If we keep increasing the number of teeth, and thus the size of the internal gear, it will complete an ever lower percentage of a single rotation, while the hole in the center always travels one full, ever-decreasing circle. And that means that we have a speed reduction. The less of a rotation the internal gear completes, while the hole in its center still does one full rotation, the greater our speed reduction. And the more we reduce the speed, the more we're going to increase the torque. As we have seen, the closer the number of teeth of the internal gear to the number of teeth of the ring gear, the greater our speed reduction was. So that means that we need the lowest possible tooth number difference to achieve the maximum torque increase. And what's the lowest possible tooth number difference between two gears? In theory, it's one tooth. But as you can see, in practice, that doesn't work. The gear doesn't fit into the ring, and that's because there's massive interference between the teeth. They start to dig into each other. In reality, gear teeth anatomy and manufacturing constraints mean that the lowest practically possible tooth difference is usually somewhere between 9 and 15 teeth, depending on the application. Okay, so teeth are useless. Let's get rid of them then. Let's use gears with rounded teeth instead. As you can see, now we have 9 quote-unquote teeth or lobes on the outer ring and 8 lobes on the internal gear. That means that we have a difference of only one quote-unquote tooth or lobe. This type of gear is also called a cycloid. So we have solved the problem of gear tooth difference. We reduced it to 1. But we still have 2 more problems. The first of those is that the hole in the center is obviously traveling in a circle, which means that we can't really just install a shaft into the center of our cycloid gear. We need this instead. This is an eccentric shaft. It's actually very similar to a crankshaft. The distance between the centers of the two journals is equal to the distance between the center of our ring gear and the circle drawn by the center of the cycloidal internal gear. This means that our eccentric shaft captures the motion of the center of the cycloidal gear while also providing us with a centrally located shaft suitable for torque input. The second problem we have is that we need to capture the slow rotation of the body of the cycloidal gear itself to use as our output. This too is easily solved with simple mechanics. We make a cycloid with holes, and then we use a circle or a plate with pins that fits inside those holes. The pins capture the slow rotation of the cycloidal disc. And what we have just created is called a cycloidal drive, which is one of the most torque-dense gearboxes in existence. This is obviously a simplified, very humble and very small, fully 3D printed cycloidal drive, but even in this form, this extremely compact little unit has an 8:1 gear ratio. The orange eccentric shaft is our input, and the blue load plate is our output. As you can see, 8 rotations of the input give us just 1 rotation of the output. An 8:1 gear ratio. Speed is reduced 8 times and torque is increased 8 times. Even a planetary gear set struggles to achieve such a gear ratio in so little space. 8:1 is actually pretty conservative by cycloidal drive standards, with gear ratios of anywhere between 30:1 to 100:1 or even higher in some cases being pretty common. They are achieved simply by increasing the number of lobes on the cycloidal gear. The gear ratio on a cycloidal drive always equals the number of lobes on the internal cycloidal gear. To put it into perspective, trying to achieve an 8:1 gear ratio with just 2 spur gears leads to this. If you use a gear train to try and reduce the diameter, you end up with 4 gears and 3 shafts, neither simple nor compact. Now, before I show you what a cycloid drive can do, and explain why it's the go-to gearbox for most of the most capable robots out there, I'd like to tell you about my personal journey in the world of 3D printing. I started 3D printing about 6 months ago using my Bambulab H2D, the printer that printed everything you can see in this video. It's my first ever 3D printer, and so far it's been the smoothest user experience that I've had in the past, I don't know, decade. But that's not what I want to talk about today. What I want to talk about is how I noticed that 3D printing is changing me, and I'm not sure what to think about when it comes to some of those changes. For example, a few days ago, my wife said she wanted a toilet paper holder here in the bathroom. And instead of going and buying one, I said, why don't I try 3D printing one? So I just designed a very minimalist, edgy looking one. It looks expensive, but I actually spent €1.30 on it in filament. After I did that, I kind of became hooked, and I started thinking that everything is too expensive, and paying 10 times as much for essentially the same thing is just crazy. So now I'm trying to buy nothing and 3D print everything. And honestly, sometimes I go too far. The last weekend, for example, I 3D printed an entire wheel balancing stand for my dirt bike. I wanted it to be solid and rigid, so I printed it using a pretty expensive filament. And by the time I finished printing it and bought the bearings, I had saved a total of negative €18. Although I printed it on Friday evening, and then Saturday morning I replaced the spokes, balanced the wheels, so I still got to ride over the weekend, which wouldn't be the case if I had ordered online, because shipping would take some time, and they don't ship over the weekend. So €18 for a saved weekend, maybe that wasn't such a bad decision. One more thing, I pride myself on using social media only professionally. I don't have a personal Instagram, Twitter, Facebook, TikTok, none of that. And so I like to think how I use my time for more important things. Well, recently I got trapped by MakerWorld. It's this site where people share their 3D printing projects, and there's all kinds of things, and you can print everything yourself. You just click on it, get the files. And there's so many cool things like, tactical vacuum cleaners, parts for your car, every fidget toy you can possibly imagine, and also every fidget toy you could not imagine. And there's so much of it, and honestly, I want to try all of it. But it's impossible to try all of it, so I then just keep scrolling to decide what should I try, and then I can't decide because there's too much of it. And then all of a sudden, an hour has passed, and all I've done is looked at other people's projects. What I think that actually is happening is that I'm just adapting to a new reality. A reality where something that was inaccessible and impossible before is now suddenly accessible and possible. If you want to try a new reality yourself, I suggest you check out Bambulab. The link is down in the description. Okay, so it has an 8:1 gear ratio, this Cycloid drive, but there's a problem. And the problem is engine balance. Actually, just balance in this case. As you see, the Cycloid inside, it's not just rotating in place. It has an eccentric motion. It's going around the housing eccentrically, which means that it creates forces, and these forces create vibrations. So how do we fix this? Well, the same way we fix a single-cylinder engine. By adding one more cylinder, or in this case, one more cycloidal gear. To use 2 gears, of course, we need a suitable eccentric shaft, which in this case looks exactly like a crankshaft of a 180-degree inline twin. And that's because we offset our cycloidal gears by 180 degrees too, so that they can cancel the forces off each other out. Let's see what it can do. This is a medium Lego motor. It produces 0.03 Newton meters of torque. As you can see, that's pretty weak. But it's still strong enough to lift this little arm which I made for it. However, as you can see, it's not strong enough to lift this measuring jug. Now let's attach the cycloidal drive and see what happens. But cycloidal drives aren't just about maximal torque increases in minimal packages. For something to be a torque god, it must be capable not just of dramatically increasing torque, but also of surviving massive torque inputs. And that's another area where cycloidal drives make conventional gears look like a joke. If you observe two gears meshing, you will notice that all the torque is usually transferred through just one or two teeth. This is why gears must be wide if they want to handle significant torque. Wider gears, of course, result in a larger and heavier gearbox. But even when they're thick, conventional gears can still be easily destroyed by shock loads or a sudden application of high amounts of torque. A nice example of this are tuned engines with aggressive torque curves. You can have the same peak torque and same peak horsepower in two engines, but the one with the more aggressively rising torque curve will blow a transmission, whereas the other one will not. Electric motors are the definition of shock loads since they can output their peak torque pretty much instantly. The motors from your average EV would easily destroy the transmission of an equally powerful combustion vehicle. But they would definitely do nothing against a cycloidal drive. In fact, many cycloidal drives are operated by some very brutal electrical motors, and yet they complete thousands of trouble-free service hours. And that's because there's no teeth to break, no gears to strip. But it's not just the toothless anatomy, it's the fact that all the lobes of all the cycloids are in constant rolling contact with all the lobes or rollers of the housing. If we have two cycloids, that's 16 points of constant rolling contact. The pins and the cycloidal gears, again, just rolling contact. There's nothing to break. Now, cycloidal drives aren't just more compact and stronger than traditional gearboxes, they're also more accurate. Traditional gears need a relatively large amount of backlash, the clearance between the teeth, which ensures proper lubrication and prevents binding, but it is this backlash that results in rotational play at the input and output shafts, and it gets worse the more gears you have in your transmission. But again, in a cycloidal drive, we have constant rolling contact at a very large number of contact points. The result is that cycloidal drives typically have virtually zero backlash, which means that robots equipped with them are capable of repeatedly achieving incredible accuracy. Even a small 3D printed unit like this one with zero bearings has surprisingly little backlash. Okay, so it's the be-all and end-all of transmissions, the best gearbox. Of course not. There's no such thing because high, impressive achievements in one field are always paid for by a compromise in another. Yes, cycloidal drives are torque gods, but they are most certainly not speed gods. The one thing they suck at is high-speed operation, high RPM. Why? Because of balance. If you maybe remember my ancient video on inline twin engines, you may recall how none of these two-cylinder or two cycloidal gear setups are actually perfectly balanced. As one gear exerts a force in this direction, the other exerts a force in the opposite direction. So the forces cancel out? Yes, but not completely. If we observe the gears from the side, we can see that there's an offset between the gears, and thus an offset between the forces. This creates a rocking couple, which is trying to spin the gears about the center. At a low RPM, the forces of this rocking couple are absolutely negligible and irrelevant. But as speed increases, these forces become larger and larger, leading to vibrations and exponentially increased transmission noise and wear. And there you have it, cycloidal drives. The massive torque increases in very compact packages, together with shock load resistance and pretty much zero backlash, make them perfect for robot arms and joints. No, they don't tolerate high-speed operation very well, but robot arms and joints don't need that anyway. So, as always, thanks a lot for watching, and I'll be seeing you soon with more fun and useful stuff on the D4A channel.